One of the applications that we will carry throughout the semester involves the relationship between distance and velocity. So we're going to take a minute to define these two terms so we can do our first application, which will be the average rate of change, to see what it tells us about these things. So distance is the measured length between two positions. So you might have one object that goes from one point to another point, and distance is the length between those 2 points. This can be measured in feet, kilometers, miles. It really depends on what you're looking at. In mathematics and physics, position is often notated using capital S of t. So if you see that within a problem, you're probably talking about position. Although we don't always use it. Sometimes we still use f of x. That is a typical way to indicate that we're talking about distance is by using the S of t. Velocity is the rate at which our position is changing. So how quickly did we get from the first point to the second point is what our velocity tells us. In mathematics and physics, velocity is often notated using v of t. So you can imagine that if we look at the average rate of change of distance, that's actually going to tell us the average velocity, or how quickly it's changing on average between the 2 points that we're interested in. So in the example below, we'll explore this relationship a little bit, but we'll see these terms carry out throughout the semester, so we'll circle back to them. So example 4. Suppose the position of an object falling off of a building can be found using the formula S of t equals 2,704 minus 16t squared, where position, S of t, is measured in feet, and time t is measured in seconds. First, find the time when this object hits the ground, then find the average velocity of this object from t equals 3 to t equals 6. So there's some interesting things happening in this problem. The first thing we want to try to calculate is when this object hits the ground. So when the object hits the ground, the position of the object will be 0 because it will no longer have anywhere to go. So if position equals 0, that means we can take our function and set it equal to 0 to find the time when this object hits the ground. By setting this equal to 0, this turns this first part into an algebra problem. So we can bring the 16t squared over to the left, and we get 16t squared equals 2704. We can divide both sides by 16. On the left it'll cancel, and on the right we'll be left with 169. If we take the square root of both sides, we get t equals plus or minus 13. Remembering that t represents time measured in seconds, time equals negative 13 doesn't make sense. So we know here that we must be looking for the positive root here. So t equals 13. So after 13 seconds, the position will be 0, meaning that this object has hit the ground. So t equals 13, and underneath it, I'm just going to notate that that is in seconds. So that's the answer to our first question. Find when this object hits the ground. Next, we want to find the average velocity of the object from time equals 3 to time equals 6. So again, we have 2 points, and we're interested in how the function changes between them. Remember, the velocity talks about how quickly the position changes. So the average velocity is the average rate of change of the position function. So here, I'm going to use S of 6 minus S of 3 divided by 6 minus 3. So that's the average rate of change of the position function. And again, I'm using S here because that's what was given to me in the problem. So if I want to find S of 6, I need to take 6 and I need to plug it into my S function. Being very careful with the computation, I'll do that in my calculator, and I get 2,128 minus, and then I'm going to compute S of 3. So again, I'm going to plug that into my calculator very carefully. By 3. When I crunch that number one final time, I get negative
144.
So now is a good time to talk about units, because in this problem, for the first time, we have some units that we can talk about this rate. So the units on the top part of my function have to do with the position. Remember, I did s of 6 minus s of 3. S of t was measured in feet. So the top part of my number was in feet, but the bottom part of my number, 6 minus 3, had to do with the time. And remember, time is measured in seconds. So my bottom number was in seconds. So that means that when I crunch these numbers together, I get negative
144
feet per second. So it's the units of the top over the units of the bottom. The negative tells me that my object is falling in the downward direction. I could be talking about tossing a ball upward, and I may have a positive velocity, but here it's going to be negative because it's falling. So here, the average velocity of this object is negative
144.
feet per second. So that means it's going to fall by
144
feet for every 1 second that goes by, on average, between time equals 3 and time equals 6.